is this topic of multi-arm bandit. And Shweta is an expert in this. She works in this area, so we are looking forward to hearing. She's a faculty at IIT Roper, and so she's visiting us contributing tomorrow. So without further ado,
So, hello everyone. So, I'm Shweta from IIT Roper, as Sushmita mentioned. So, today I'm going to talk primarily about multi-arm bandits. So, the way I have organized my talk is into three parts, which is three lectures over the period of this day. So, today in the first lecture, I'll give you a very basic introduction of what multi-arm bandits are, what are the reward structure, and we will focus on what is meant by stochastic rewards, and when these stochastic rewards happen, what kind of algorithms, what kind of solutions that you apply, and what is it that you are seeking, right. The second part will be more of a research oriented, just to give you a flavor of what kind of application do we use where multi-arm bandit is important, and specifically its connection to the auction theory, which you would have already seen in the summer school, right. So, we will see its connection with the auction theory in the second part of the talk. In the third part of the talk, I will again talk about multi-arm bandit, but with a very different reward structure, and I will try to tell you its connection with respect to two-player zero-sum game, and tomorrow when we do cooperative game theory, then some connection with the correlated equilibria. So, this is how the talk is going to be organized. Again, I will try to be really at the basic level and try to build up the things, but while I am telling something, and if I skip something, then please feel free to ask questions whenever you have, right. So, let us start. So, before starting, let us try to see what exactly is a multi-arm bandit problem. Let us just try to understand this problem. So, in the morning I got a question, why your problem is called the multi-arm bandit problem. So, as the name suggests, there are three components to it. One is called multi, which means many. Armed means arms or some options, and bandit is some kind of a gambling scenario or a gambler, right. So, this problem is called multi-armed bandit problem because it is inspired by the scenario of a gambler who is going to a gambling gambling room, and he has multiple slot machines available to it, right. So, he has this slot machine, this slot machine, this slot machine, and the idea that and the question that this gambler is asking whenever he is going to this casino is which slot machine he should play on. This is a simple question, right. So, I am going to the casino every day, I am seeing so many slot machines, and I want to basically decide which slot machines to sit so that I can get the maximum reward. So, every time I pull the arm, I am putting my money to pull the arm, I may actually get some reward out of it, or I may get nothing, right. Whatever money I have put, it might just get lost, right. So, similar scenario. So, I have n options every time, and then each option if I take, it gives me some reward, and the primary issue here is that suppose if I am going and I play on this machine, okay, then I can only understand or I can only get the feedback of this machine itself. I will never ever know whether these machines, how much capable or how bad these machines are. I will only understand the reward for that particular time for the machine on which I have played on. Okay. So, this is what is mean by only exploration of an option will reveal the reward of that option. Until and unless I pull that arm, I will never even know what kind of reward structure that particular arm is. Does it make sense? Perfect. Okay. So, before going further, why are we even worried about gambler, right? We are not gambler, of course, right. So, why are we looking at this problem? So, before even understanding the nature of this problem and the algorithms to solve this kind of a problem, let us try to understand what kind of applications it has, right. So, the first application that I will come to is called the sponsored search auction. So what happens in the sponsored search auction, and you will see a lot of this in my second lecture, but let's try to understand what this application is. So everyone knows Google search auctions. So the idea is basically whenever I search for a keyword camera, let's say on the Google, what it does is that Google basically, apart from showing all the result, it also shows some ads here, right? So I searched for camera, I got these results, some Wikipedia, Flipkart results, but apart from that I also get some advertisements. Okay. So now what Google does is that it basically, it has some auction space available to it, and what it does, it is basically it auctions these advertisement slots. Okay. So it basically asks, for example, Nikon and Canon and all those companies to basically bid for this slots. Okay. And what happens in auction when somebody bids? So the allocation is, for example, the VCG auction, what happens? Sorry? The highest bidder gets the object and the payment is the second highest. Okay, you understand your logic concepts here. So good to know that. But so this is also what will happen here. You know, I am bidding, and then if I give the highest bid, I will get the space and I will pay the second highest. There is nothing fancy about here, right? So why is it multi-arm bandit important here? So the complication comes when even though if Google is showing the Nikon ad, Google only gets the payment only if somebody is clicking on this ad. Okay. So for example, if Nikon is placing $10 bid and Canon is placing $5 bid, it's not like Nikon will get ulta, right? So because this is the reverse bid, the lowest get the ad. So Nikon is placing $5, Canon is placing $10. So it doesn't happen that Nikon gets the $10 like VCG happens. But what will happen, Nikon will get only money when somebody is clicking on this ad. Does it make sense? Yes. Okay. So VCG will not directly work because I also need to understand how many clicks Nikon will get and how many clicks Canon will get. And how will I get to know that? I will get to know that only when I am placing these advertisement in these slots. Okay. If I don't see Nikon and Canon, then how am I supposed to click the ad? Okay. So now you understand the dilemma that Google is facing. Okay. It needs to show some ads to find the click-through rate. Until and unless it shows it, it doesn't realize what the click probability is. Okay. And therefore it cannot run an auction. Does it make sense? Perfect. So this is one of the primary example. So again, the similar examples you can just continue, right? So ad auction is one. The second good example is called the crowdsourcing area. What happens in crowdsourcing area is the following. You have a requester who wants to basically get some job done, and what he is trying to do is he is trying to post this task on the crowdsourcing platform, and then lot of experts or workers are available over the internet to do this task. Okay. Now for the task to be done, this particular person has to pay these crowd workers, but it also has to maintain some integrity of the task. So some quality has to be maintained. Okay. So similar dilemma, until and unless this task is given to the crowd workers, it won't know what is the inherent quality that these workers will have, and therefore it needs to face, every time it needs to understand what is the quality and what kind of payment should be made to these workers. Does it make sense? Perfect. I'll come to the smart grid example later, but this is a general trend. So the general trend is the following: in any application where there is some uncertainty involved, basically learning, as well as you have lots and lots of options, you are learning what is the quality of the options, and then in such scenarios you can basically apply your multi-arm bandit application. So there's huge, there is recommendation system, there is reviewing website. It started with clinical trials, IoT game, and so on and so forth. So I hope the motivation is clear. Any questions?
So the learning, this thing when you say that any situation, application where learning is involved, what you mean is uncertainty, right? When the ground truth has to be learned from the market or from the agents.
Yes. Now these uncertainties could be of various types that we will understand what kind of types are right now. So today, at least for the first talk, I'll be focusing on something called the stochastic reward setup. I'll explain that. But it's typically you have lots of options, and whenever you take a particular option you get some reward out of it, but you are not sure whether every time you get an choose this option this is a fixed reward. So that is not going to happen. It will change over a period of time. Now how it will change will basically result in a different types of map problem. Any other questions? Okay, perfect. So now there are three fundamental types of multi-arm bandit problem, like Sushmita asked. There is something called stochastic multi-arm bandit, adversarial multi-arm bandits, and Markovian multi-arm bandit. Let me just give you a quick glimpse of what these multi-arm bandits are with some application, and then we will continue in the first lecture. We will continue on the stochastic multi-arm bandits only. Okay. So what is a stochastic multi-arm bandit? Again, go back to your casino scenario. You have lots of arms available to you, arms or options. Okay, you pull a particular arm or you take a particular option. Let's write it as arm IT. That means the arm that you have chosen at time t. And what happens is the reward of this arm basically comes from a fixed distribution. So what do I mean by fixed distribution? Each and every arm has some fixed reward distribution. It may be Gaussian, it could be Bernoulli, it could be any fixed distribution with a fixed mean. And whenever you pull that particular arm, you get a sample from that fixed distribution. So you basically observe the sample. Okay. So there is a fixed distribution associated with each and every arm, and whenever you pull the arm, you don't get to know this distribution, but you only collect the samples of this distribution. Okay. And what you want to do? You want to basically learn which arm has the best distribution or which arm is capable of giving you the best reward over a period of time. Okay. So in stochastic bandit, what you get is the reward XITT, which is nothing but the sample of the reward distribution associated with arm IT. Make sense? Okay. So this is stochastic bandit where the rewards are stochastically generated. Perfect. Okay. So this again is basically application is again the ad auction that we sponsor search is one of the option. Okay. So most of the cases are falling into the stochastic bandit setting. Okay. Then the second setting is called the adversarial bandit setting, which is more related to the game theory, and we will see it in the third lecture. So what happens in adversarial bandit setting is whenever you pull an arm or you take an action, you don't get the reward of that particular. So it's not stochastically generated. There is some adversary sitting who basically define what would be the reward of that particular arm for each and every arm. But the reward that you get to know, again there are two setup, full bandit or the semi bandit feedback. In one of the bandit feedback, what you get, you basically only receives the reward of the arm which you have pulled, but this reward is adversarially generated. What do I mean by that? So suppose I have arms 1, 2, 3. Okay, At time t equals to 1, let's say you pulled the arm 1. This is the arm you have pulled. So what adversary will do? Adversary can basically decide the rewards of these arms adversarially. So what it can do? It can actually give the reward of 0 here and then reward of 1 1 here. Okay. So you would think that instead of choosing the arm 1, you could have chosen arm 2 and arm 3. But you don't know, you don't observe these. You only observe that when I pulled arm 1, I get the reward of 0. Okay. Now what will happen? At time t equals to 2, you might think that at time t equals to 1, I pulled arm 1, but I got a reward of 0. Then in this time, let me pull arm 2. Right. So if I pull arm 2, then again what will happen? Adversary who is sitting here would again generate the reward. Okay. This time what it can do? It can put the reward of 0 at arm 2. So whatever you are pulling, it can basically, it has the full flexibility to put the reward of 0 to whatever arm you are pulling.
But it's
Yes. Yes, so we will see it in the third lecture. Everywhere if you pull 0, the kind of, we are basically, ideally you want to maximize the reward, but because adversary is putting all 0, the maximum that you can achieve is 0. So that is also best. Okay, so then the kind of performance metric that we are looking at is just not the to maximize the reward, but what we do is we give some kind of a regret notion. How do we compare against the best person who could have done? Okay. So putting 0 is not a good, because then I can pull anything and I will still be okay because I am still comparing against the best. If everybody is bad, it does not matter which one I choose, right.
So the adversary's goal is to keep my reward as low as possible.
Yes.
So this is why adversary should put non-zero values in some arms so
So that
can indicate loss for me.
exactly.
If I don't do
So you
that.
basically capture the loss that you incur. Okay. However, just a minute. However, this also tells you that you cannot basically get rid of this adversarial bandits by minimizing loss, but by just doing some deterministic algorithm. Okay. For example, in this case, in the t equals to 1 case, instead of basically choosing one particular arm with full probability 1, if I would have said I will pull first arm with probability 1 by 3, second arm with probability 1 by 3 and third arm with probability 1 by 3. Okay. Then no matter where this person is putting the reward on, I will at least get the expected reward of 1 by 3.
I think the model is not very clear to me. So R1 is like 1, 2, 3 are 3 different distributions.
Okay.
Like 0 is with some probability.
So this is adversarial thing that I told you. So this is adversarial reward setting. Okay. The first setting which I told you is called the stochastic reward setting. Okay, okay, let me give you this example as well. So these are the two reward models. So again I have the arms 1, arm 2, arm 3, and for the sake of understanding simplicity, let's assume that each arm is basically has some fixed Bernoulli distribution. What is Bernoulli distribution? 0 or 1 with some probability. Okay. So with 1 I associate the probability mu1, with 2 I associate the probability mu2, with 3 I associate the probability mu3. Okay. In the stochastic reward setting, what happens? At t equals to 1, again I decide which arm to pull. Let us say I decide arm number 1 to be pulled. Okay. Then what will happen? The reward of this arm 1 will be what? It will be 1 with probability mu1 and 0 with probability 1 minus mu1. This is the reward that I will observe. Okay. So it could be 1 with probability mu1 and 0 with probability mu2. Okay. And if I similarly the other. So here it is not adversarially, here it is generating through this stochastic thing.
So in the adversarial, is it the case that the mu1, mu2, mu3 is not set previously, the adversary is trying to define every time new mu's, or is it that there is no probability at all that
There is no probability at all, it is just generating the reward, but rewards are bounded. So, they are generally assumed the rewards to be between 0, 1. Okay.
When a player plays an arm, does he know what things he'll get if he plays other arms at
No.
that specific time?
No. In the bandit feedback, it gets the reward only to the arm that it has played. Nothing else. That makes the problem interesting. Okay? Okay? It's perfectly fine if you don't understand Markovian bandits, but for the completion, let me tell you what happens in Markovian bandits. Again, you have, let's say, 3 arms, 1, 2, 3. Okay. So, are you familiar with MDPs? Markovian decision process. Okay. So, let me tell you this thing. So what happens in the Markovian, because Aparna may talk about it. So, what happened here is, let's try to understand this with an example. Suppose I have an arm, I have an option or an arm or an action. It has only 2 states, either it could be good. In this case, for example, either the action is giving me the reward of 1, or it could be bad. Okay. So, either the reward could be good or it could be bad. Okay. So, what happens in Markovian bandits is there is something called the transition probability matrices associated with these action spaces. Okay. So, that means let us say this is for arm 1. Okay. So, what will happen if I pull arm 1 and let us say it is in good state, okay, then with some probability it may shift to bad state.
What does it mean for it to be in good state? Like we don't see what's the number of it.
Sorry?
Do we see 2 numbers, like what was the number before and what was the number after? Like in the machine, do we see 2 states? I mean, before pulling the lever, do I see it stays good? Like this.
So, it is like this. So, suppose if you are pulling a lever and it gives you a reward of 1, okay, then what is the probability that next time also it will give you 1? So, understand it this way. Okay. So, in restless bandit recently they have been applying it to the medical intervention application. So, in medical intervention, let us assume you have depression cases, okay, and you have the patient's mental health that you need to cater. Okay. Now, there are 2 options whether to intervene for that patient, as in whether to call that patient to ask about his health or not to call. Okay. Now, what happens is, let us say I have 100 patients, definitely I cannot call 100 patients every day, I need to decide which patients to choose. Okay. In such application, each patient will have some health thing. So, either it could be in the good state, good mental peace and everything, or it could be in the bad state. Okay. If I give a call to the patient, there could be some possibility that this patient may shift from good state to the bad state. Okay. Similarly, if I call a bad patient with bad mental health, then it might shift from bad to good. Okay. Good patient, with some probability it will stay in good, and with some probability it will stay in bad. Okay. In Markovian bandits, what happen is we try to basically pull those arms such that maximum of these arms stay in the good setup, something like that. Okay. So, these probability transition, these are called the probability transition matrix in MDPs. These are basically known. Again, so even if you do not understand, it is fine, but it is good to know these terms when you encounter, so that you understand whenever you are doing some problem that this part could be utilized. Okay. So, it is perfect, because we will not be covering this in the entire day. Even if you do not understand, it is perfectly fine, but just it is good to know that these kind of things are there, okay, to help you out in some of your research. Okay, any questions? Yes, please.
Stochastic bandits, like that was a common distribution for each of the arms?
No, it was different, right? So, for example, this particular, are you able to see from there? Okay, so here when I took Bernoulli distribution, the probabilities were different. So, for arm 1, it gave me the reward of 1 with probability mu 1 and 0 with probability 1 minus mu 1. Similarly, arm 2 gave the reward whenever you pull this arm, then it will give you 1 with probability mu 2 and 0 with probability 1 minus mu 2. Okay, so every arm has different, that is why it is interesting. If everybody has same thing, then no matter what, because you are eventually you are maximizing the expected reward. Okay, so in this case basically what you want, let me give you slightly ahead. So, what you want, so suppose mu 3 is the highest among mu 1, mu 2, then ideally in order to maximize the expected reward, you will basically end up in choosing arm 3 every time. That would give you the highest expected reward, but the issue is you do not know mu 1, mu 2, mu 3. Okay, that is the issue. Okay. So, multi-arm bandits are, as I have already told you, they are famous for something called the exploration exploitation dilemma. So, what is exploration? Exploration is choosing the arm which you want to explore. Okay, you do not have enough information about them, you are exploring to gather the enough information, and exploitation is something when you are choosing the arm in order to maximize the reward. Okay, let us take an example. Suppose you have two arms, each arm can either give you 1 rupee or give nothing. Arm 1 gives reward 1 with probability 80% and arm 2 gives reward with probability, sorry, it should be 0.8 and 0.6. Okay, so arm 1 gives reward 1 with 0.8 probability and arm 2 gives reward 1 with 0.6 probability. You do not know these probabilities, you can only pull the arms and know the reward. And let us say because you do not know this, you end up in choosing arm 2. Okay, arm 2 gave you the reward, first time you pulled it gave 1, second time it gave 1, third time 1 and so much and so forth. So, then the question that you are asking ki, you know, arm 2 has given me reasonably good reward, should I continue choosing arm 2 or should I switch to arm 1? And suppose you say, okay, first time let me see what is the arm 1 doing, and then you pull arm 1 because there is a 0.2 probability it gives you 0, it ends up in giving 0. Okay, should you continue arm 1 or should you switch to arm 2? Okay, so this is the exploration exploitation dilemma that I am talking about. Yes.
Do I have a limited number of turns? Like total?
We assume there is a total limit of capital T. Okay. So, what is the goal? The goal is to maximize the reward over a period of time t, and as I mentioned, in stochastic at least you can talk about maximizing the reward. It does not make much of a sense if you go to the adversarial bandits like Pallavi pointed out. So, what you do basically is to minimize the regret. We will see what the regret is, but intuitively the regret is the same thing that I was talking. Regret is what is the reward that your algorithm, your online algorithm is getting compared to the reward the optimal offline algorithm is getting. So, what do I mean by offline? The algorithm which knows everything. Okay. So, when I talk about optimal offline algorithm, I am talking about the algorithm which knows everything. So, in the stochastic bandit setting, it knows mu 1, mu 2, mu 3. Okay. In the adversarial bandit setting, it knows what are the rewards generated at each and every time for each and every reward. Okay. So, here what is the optimal algorithm doing and what is the optimal algorithm doing compared to what you are learning. Okay, and I take the difference. So, obviously the reward optimal offline algorithm reward will be highest. Okay, you take its difference with the reward that you are getting, that will give you something called the regret. Okay. And when I say you want to minimize this regret, that means you want to maximize your reward as much as possible. Make sense? Perfect. Okay. So, now at least in stochastic multi-arm bandits, there are two setup. Okay. I will talk about both the setup, but let me just give brief summary. So, one we understand, first one we all understand, are we so far so good? Okay. The second setup is slightly different. In the second setup, what I am looking forward is not to maximize the reward, but to find the best possible action. I mean, you would see they look similar, it is just the goal wise they are different. Okay. In the first setup, I want to maximize the total reward no matter what arm I pull. In the pack learnability setting, after a certain time, I want to tell that with high probability this arm is almost best arm, something like that. Make sense? No? Yes? So, how do you quantify almost optimal? Just give me some, have you heard about this almost optimal or close to optimal in some algorithms course?
We can set a threshold and determine it.
Exactly. So, when we say close to optimal, what we say is that let us say optimal is 0.8, okay. Then close to optimal will be epsilon close to 0.8. Okay. So, we set a threshold here also. Okay. I will define the formal notation after some time.
The second point is the situation when we stop exploring and start exploiting. Is that so?
Similar, yes. Yes. Okay. But second situation is more like when you are more worried about, you know, who will be the best person after some time. Okay. Okay, perfect. Okay, so let us focus on the first thing. What is a regret notion? We have n arms and capital T rounds. At each time I pull the reward, I receive XITT. Now again, for the sake of, because this topic is very new to everyone, we will keep it very simple. We will assume that rewards are either 0 or 1 for the sake of understandability. Okay. But whatever I am talking, you can easily extend to any reward function between 0 and 1. Okay. But for now, I will assume Bernoulli distribution 0 or 1. Okay. And the total accumulated reward is basically whatever reward you get and you sum it over T. Okay. Now, as I said, what is the regret? The first term here, okay, the first term here basically denote what is the maximum reward that you could have achieved. Okay. So, what you want is you basically, this is the first term that you could have achieved, you basically take max over I and find which arm would have given you maximum reward over a period of time T. That is your first term minus whatever you are achieving. That is the second term here. So, regret is simple, whatever the optimal algorithm would have achieved minus whatever you are achieving. Okay. In the stochastic setting, because these are generated 0, 1, I really do not, this does not make much of a sense, because otherwise I can be really bad, as we talked about in the adversarial setting. So, I basically try to minimize my expected reward. Okay. So, when I do expectation, take just expectation here. Okay. The problem now is that this term is not easy to minimize, because max and expectation are not interchangeable. Okay. Before that, if in the same example I have mu1, mu2, mu3, just to confirm what is expectation of x1t, it will be mu1. Okay. Just confirming. Okay. So, expectation of x1t will be mu1, expectation of x2t will be mu2, and similarly expectation of x3t will be mu3. Okay. So, if this is interchangeable, then my life would have been easier, because then I can just linearity of expectations, I could have just pushed expectation inside and then I could have got expectation of xit, which is mu1, mu2 or mu3, whatever it is, right. But this is not interchangeable. So, what we do is, instead of minimizing this, what we minimize is something called the pseudo regret. Okay. What is pseudo regret? In pseudo regret we switch. Okay. So, we make max here and expectation here, and mathematically again let me not spend time, although I wanted to, but mathematically you can prove that this regret will be upper bounded by this regret. Okay. So, you can prove that pseudo regret is less than or equals to expected regret. But what we will do? We will try to focus on this regret. So, now I want to minimize this regret. Because I have interchanged it, the first term is easy to find. Okay. So, what is this? It is nothing but expectation. So, this is something which is algorithmic specific. Max over I, expectation of xit will be nothing but mu I. So, it would be basically with mu I. So, for the arm 1 it would be capital T into mu 1, for arm 2 it will be capital T into mu 2, for arm 3 it will be capital T into mu 3. Is this okay? Please let me know if I am going too fast. Sorry? Questions? You had something, right?
So the notation I was asking about, so in the first one we have summation xit, so this I is representing, it will give me the arm which has maximum reward in that round.
No, arm I is not in that round, right. So, it is max over I, this summation, right. So, for I is equals to 1, you find what is the reward that arm 1 would have given if I would have pulled it over capital T rounds. It is not summation ke andar max.
So each arm we are checking for T rounds, so whichever arm is giving me the maximum reward in
that's what it means, right. So, max is outside summation. So, that means you are basically summing it first and then finding the I which is maximizing that summation.
And this I subscript T in the next one, what does that mean?
That means IT, remember that notation, IT is the algorithm that you are doing, right. So, this regret, when we are saying, it is basically corresponding to an algorithm which is outputting an arm IT at time t.
So, this one is showing whatever arms we chose in each subsequent
Whatever
round,
reward that
false
you
reward
get.
minus the whatever maximum we could have got, but this is choosing only one arm every time, right?
Yes, and you are choosing differently. Yes. Okay. So, what we are doing is we are comparing our algorithm against the best possible single action that is available.
So in other settings, you can't do this max.
No,
It would
in
be-
the adversarial you can't.
Like we cannot
we will
take
come back to it.
multiple arms, like say I will choose this arm 20% time, 80% time, maybe.
Depends on that.
Even then you would take the expectation, right. So, if you are, so let's say if you are pulling, anyways that is what you are doing, right. So, let's say you have capital T rounds and you have 3 arms, okay. What you are doing, you are dividing your T in 3 different things. Let's say this is 70%, this is 20%, this is 10%, okay. Then your reward is what? 0.7 T into mu 1 plus 0.2 T into mu 2 plus 0.1 T into mu 3. This is your expected reward. So, either you define it from the probability perspective or you do it like this, but ideally we are talking about the expected reward.
Like in the real, say casino games, the probabilities would be changing there, right, for each arm or like,
Not necessarily. It depends, right. So, what is the rigged probability of each and every slot? I am not going to change every time machine, right. So, people may get to know which arm is better over a period of time. That is a different thing, ki you won't be staying too long in the casino, right. So, long enough to find, right. And also these probabilities are not too high, right. If some machine will have it will be less than 0.5, let's say, right. So then anyways half of the time you are losing, so then also casino is making profit. Okay, I think we have done this. We have done this. Okay, so let's just try to write things differently so that we make some attempt in solving the problem. Okay, the problem is simple. I want to find the best possible arm with least exploration as possible, so that I do not lose too much on the regret. Okay, that is the problem. Okay, so what is the pseudo regret? Pseudo regret is T mu star. So here I am denoting mu star by max I over mu I, and I star is the best possible arm. In this case, if my arm 3 is the best, that means mu 3 is better than mu 2 and mu 1, then mu 3 will be my mu star and arm 3 will be my I star. Okay, and the pseudo regret will be T into mu star minus summation of mu I t, because I pushed expectation inside. So this was my definition. Okay, with linearity of expectation I can push expectation inside. So this will be summation over t, t equals to 1 to capital T expectation of xit, which will be nothing but mu I. So this will become t into mu I minus t into mu it, not t into mu it, summation will be still there because I am choosing different arm. Okay, now when I do max over I t into mu I, that would be nothing but t into mu star. Okay, and the second term will remain, and that would be nothing but mu it. Okay, so that is how I can write. Is this okay? Perfect. Now some more notation so that we understand this problem slightly more closely. Like, remember this diagram. So what I can do, eventually I am talking only in terms of mu i's, right? Which arm gave what reward at any time, I am not too much interested in it, because the rewards are generated stochastically. What matters is their mu i's. I am taking the expectation. Okay. So what I can do is that for each algorithm I can say how much time this algorithm has pulled arm 1, how much time this algorithm has pulled arm 2, and how much time it has pulled arm 3. Okay. So let us denote capital Ti with that.
What was this mu here in the summation, inside the summation?
This mu it is the same thing, right? So if I am pulling arm 1, then it will be mu 1. If I,
So that is a changing mu, right? Whichever arm we are choosing.
that's why it's it here, right? So it's mu subscript it, because mu chota hai to I bada hai, to isliye it's not visible. Okay, it's mu subscript it. Yeah. Okay, so this is changing, that's why you cannot change, get rid of this summation. Okay, so Ti is the number of times you are pulling an arm I. Okay, and what is delta I? Delta I is basically how much loss you incurred by pulling the arm I. Okay, so it is mu star minus mu I. Okay, then this regret will be what? It would be nothing but sum over all the arms. Okay, Ti into delta I. Is it okay? So far so good. Okay. Now because your algorithm is typically not deterministic, so this Ti is not deterministic, you basically, like somebody was saying, you take the expectation over the algorithm for Ti. So you include the randomization of the algorithm. Okay. I will give you some time to get into it. Hanji. So because your algorithm is not, so you might have an algorithm which is probabilistic, so it will not always end up in pulling exact Ti amount of time. It's like somebody pointed out, right? So at each time, so imagine an algorithm, at each time it is pulling arm 1 with probability 0.7, arm 2 with probability 0.2 and arm 3 with probability 0.1. Okay, then every time you run this algorithm, Ti's will be different because it's a randomized algorithm. So then you take the expectation. So in this case, it would be whatever I had written on the board. Okay.
That pseudo
second, last second. Yeah, isn't it just for one round like that?
No, it's TI, right? It's TI. So what is TI?
Oh, okay.
TI is the total number of times I have pulled arm I till capital T.
It's exactly what you have.
Exactly. It's exactly same. I'm just taking expectation over algorithm because algorithm could be randomized.
Because that mu star is an expected optimal value, so is it possible that delta I can be positive even though it should always
No, I defined mu star with max I mu I, right? So because see, reward difference could be negative or positive. So it might happen that at the time t, if you would have pulled arm 2, you would have got reward 1 and arm 3 would have given you reward 0, whereas arm 3 was the optimal as per your definition. So the reward could be negative, yes, because it's a stochastic setting. But what I am saying is that I am trying to maximize the expected reward and therefore expectation may it will be positive. Okay. So now what I want to do, I want to design algorithm. So I got a problem, I mathematically know what I need to minimize, what I need to maximize, optimization problem is clear. Now let's turn to the algorithm. Okay. So the first algorithm is called the greedy algorithm, and greedy algorithm works on the following principle. It's simple, okay. So every time you are pulling the arm or taking the action, you are basically getting some samples out of it. So in some way the statistics tells us that if we take the average over a period of these samples, and if we get large enough samples, then we will get as close to the optimal thing as possible. That's the principle, okay. The primary thing is, because you are generating the samples, you collect enough samples to gather how close you are to the optimal. That would be the driving force of from here onwards. Okay. Now the reward, how will you compute the reward? You will basically take the average. Okay. Average of what? Suppose I want to find the estimated reward of arm A. Okay. That would be what? That would be summation over how many times I have pulled arm A divided by, how many times, this denominator is how many times I have pulled arm A, and numerator is out of those times how many times it has resulted in reward of 1. It's just the empirical average.
The expected reward for pulling arm A is the numerator. Expected reward for having pulled arm A.
It's not expected reward, because you are not observing mu A, you are just observing the rewards 1 and zeros. Okay. So now in the entire time duration capital T, you basically see at these times I have pulled arm A, and basically out of these many times, how many times you got 1. So that is the numerator. It's the cumulative or empirical average, that's all. Okay, and that gives you some idea. Okay, and the greedy algorithm, what it should do is, so suppose you have some estimates about all the arms, then if you were to design greedy algorithm, then what you would have done? You would have simply chosen which arm has the maximum cumulative reward. Yes.
So basically, I'm treating this cumulative reward as if the learned expectation.
Exactly. And they become better and better as you get more and more samples from some bounds.
But we still haven't figured out how many rounds of exploration we need to do at experimentation.
I am coming to it. Okay? Yes. Okay, perfect. But greedily it would have worked, but as we understood well now, these estimates could be really bad if we haven't chosen the arms well enough. I'll skip this, I don't think it's relevant. and I will just give you some idea about this. So, what epsilon greedy algorithm does in this room, every one of us understand that the exploration is important. What epsilon greedy algorithm does is a very simple strategy. It defines a parameter called epsilon. Okay, at any round t, it could be variable over a period of time also, right. So, at any time t, it with probability epsilon t or epsilon, it will explore. It will just randomly pull some arms. Okay, and with probability 1 minus epsilon, it will exploit. This is the simplest algorithm. Okay. Whatever is, so you are maintaining this QTA. Okay, so basically this slide is just an efficient way of computation, so that's why I am skipping this. Okay, so with probability 1 minus epsilon, you pull the arm whichever has the best cumulative performance so far, and with epsilon it is doing. It performs reasonably okay in practice. It's a simple algorithm and it performs reasonably okay. Yes.
In this epsilon 1, this random action that we are taking, so will we consider the arm that currently has the highest
no,
QT, or
with epsilon probability, if I have arm 1, 2 and 3, with 1/3 probability I will pull 1, 1/3 probability I will pull 2 and 1/3 probability arm 3.
Currently if one has say 7.7 probability, still I will, like, that is random.
That's what exploration means, right. Even though I understand that this may be better, then also I basically still do some exploration.
We have 3 paths. I know this is the best till now, but still I might choose.
But
this.
you might not be very confident in it, right. So, in order to improve this, what you can do, again similar to your intuition, see, initially I am not so much confident, right. So, initially I do not know anything. So, what will you do? For the initial rounds, you will basically explore with higher probabilities. Okay. Therefore, I said variant of epsilon greedy is you make this epsilon variant over t. As you go more and more deeper, more and more, you basically reduce. So, a typical example of epsilon t is 1 by t. Okay, so it reduces over time.
Why have you picked an arm like probability, meaning, so you decided to explore with probability epsilon.
T, yes, epsilon.
So now to which arm to explore? Why do we need probability over there? Can't we just round robin every round, like?
That also you can do.
Because if we do probabilistically, then there's a chance that.
Because you are giving equal probability, the chances of one getting favored over other is not much.
But I can get rid of it if I just manually making it.
You can do it. As I said, you can do it, but you just have to maintain key which arms have been explored, these last explored. That's all. You could do it. I am not denying that fact. It's just a simple exploration and it does not have any regret. So, regret guarantees also will not change. You can do it, not an issue. Okay, because the way the regret guarantees goes is that with epsilon probability you are anyways incurring the regret. You choose it round robinly or you choose probabilistically, it does not matter. Okay, so regret guarantees will have no effect of this. Okay, good. Okay, I will skip this because I want to basically tell you the best part of it. Okay. Okay, so that was a simple thing, but there were some issues. Okay, what were the issues? So, good algorithm, very simple, with epsilon probability you explore. Okay, however, imagine a case where you have this mu1, mu2, mu3. You know mu3 is best, mu2 is second best, and mu1 is the last. Okay. Ideally, in the ideal world, what you would like to do is, if the reward difference between mu1 and mu3 is too high, let us say mu1 is 0.1 and mu3 is 0.8, okay, then logically, statistically, you will need lesser samples to understand the fact that this arm is much better than this arm. Okay, if one coin is biased with 0.8 and another with 0.1, you will need lesser samples to understand the difference. Okay, then epsilon greed seems to be a waste of time, even though epsilon, and suppose this mu2 is 0.7, this mu2 is 0.7, this is 0.1 and this is 0.8. Okay, it's very easy to identify that this one is a bad person. Then why should I spend time in exploring this person? I should rather give the exploration time to this person whom I am less confident about.
But 0.1 and 0.9 is same number of samples. If one lever is 0.9, suppose mu3.
Mu3 is 0.9, okay.
Then deciding that is good, the number of samples I need, is same as deciding that this is bad. I will just
It's a comparison, no, between 0.1 and 0.9. We are just trying to.
So basically what you can do is, let me go slightly ahead, is that you can basically what happens is the difference between the expected and this thing, you are right. So basically whatever the cumulative I am getting with this and whatever the cumulative I am getting, उनके बीच में difference is the similar number of samples, but I am not comparing the cumulative of this and this. I want to compare cumulative of this and cumulative of this as compared to these, right? So that way I will get to know. It will be clear in some time.
You're saying that we'll waste our time exploring if there's a less difference.
Not exploring the, you could have explored a better option as compared to this. That's what I'm saying.
But we can just change the epsilon function, right? We can make it close to 0 quickly as the samples go up.
That doesn't work. Again, I'm not talking about, I'm not saying that exploration is bad. I'm saying if you have 100 arms, I'm talking only about 3 arms here. Imagine in a situation where you have 100 arms, okay? You are basically ending up in exploring 99 arms with this, even though epsilon decreases. If epsilon decreases sharply, it doesn't help in regret. In fact, it worsen it, because exploration is absolutely necessary in multi-arm bandits.
Between them the probability is same, but
between the arms I am saying, right, if you can identify much earlier that this arm with high confidence is not a good arm, then you should not waste your time in exploring that.
basically round robin is inefficient. You are figuring out better.
Exactly,
probability.
round robin or giving the equal probabilities to all the options.
So we have to decrease the exploration space as we go on
Exactly,
every time.
right.
Can I go to the previous slide where you had the epsilon? I'm adjusting QA as I go along.
So as I said, this is the map
Yeah.
where you adjust. It's very simple, you just write
Right,
QM
right.
with respect to
Some kind of adjustment has to happen because this information that one arm is giving me very low reward only comes across when I adjust the cumulative reward. Right? When I see the cumulative reward coming from the arm 1, I see it's very low compared to the cumulative reward coming from arm 2 and 3.
Yes,
That is what allows me to discard
exactly.
arm 1.
That is the principle of our next algorithm.
Okay, so this is why having a very fixed way of exploring things,
It doesn't,
it does not work.
Malab, it works, but
Actually,
it
this take-
doesn't
yeah,
give
it-
you the
it-
efficient things.
You want to put higher emphasis on things that are giving you better reward.
Okay, perfect. Yes, we do that. That's what makes it interesting. Okay, so okay, we understand it. Let me skip it. But what Sushmita just pointed out is actually the heart of our next algorithm. You have to capture the fact that how much cumulative reward you have taken, and you need to basically explore also. Okay. In some way, if we can combine this exploration along with the cumulative reward, then we might have some hope to get a better algorithm. Okay. This is what our algorithm, which is optimism in the face of uncertainty, does. Okay. It is a pretty nice algorithm, very intuitively. So, imagine this picture is doing what? It is basically these blue, so it has 1, 2, 3, 4, 5, 6 arms, okay, and these blue bars basically denote the mean reward of the arms, which you do not know. Okay. So, these blue are the rewards which you do not know, these represent the mu i's. Okay. What you basically do, you say that initially you do not know anything about the arms. Okay. So, you basically start with the fact that everybody is good. Okay. So, what you do, you basically maintain something called an optimism for each and every arm. This is called upper confidence bound also. Why it is called, we will come to know in some time. Okay. So, you say that everybody, if I pull, is capable of giving me the reward of 1. Everybody's mu I is 1. Okay. With this optimism, you pull the arm. Okay. Let us say you pull this arm and you get a reward of 0. Okay. Then what you do? You reduce its optimism. Okay. And then you continue on this. Does it make sense?
This is exactly computing queues. What is different?
No, the difference is how I am maintaining this bounds.
You are maintaining two probabilities now. One is the blue lines is queues.
Blue line is queues, and what I will be doing is on these queues I will be adding some exploration term, which basically will give me this orange bar. Forget about this bar right now. Okay, so forget about the pessimistic thing, I am just talking about the optimistic thing. So, on these average reward that I am maintaining, I will be adding some term so that I can basically say that this is the best possible scenario for me. And the way I am going to maintain is the following. Okay. From the statistics, what I will do is I can find the bound such that within these bound, my average reward will lie with high probability. Okay. So, based on the number of samples, what will happen? These bounds will basically shrink towards the true mean. Okay. So, if I have lesser number of means, that means optimism will be highest. If I have lesser number of exploration of that arm, that means optimism will be highest. Okay. And as I go on exploring, this will basically converge to the true mean. That is the idea. It is simple. Okay. So, now just have it in mind. Let me just take a slight detour and tell you about the Hofstad's inequality. Have you heard about it? No. Okay. 2 people. Okay. So, this is again coming from statistics, and it is okay if you do not understand the math, but intuition is what I told you. Okay. So, what is x bar? X bar is basically what we defined, right. So, xi divided by n. If n is the number of times that I have pulled arm I, then summation of xi divided by n is nothing but the empirical reward that we are talking about. Okay. And what that is x bar. Okay. And what would be the expectation of x bar? It will be nothing but mu, jahan se xi aa raha hai, right. It will be nothing but mu. Okay. So, the problem is here mu 3 was 0.9. Okay. But what I know, I have just taken the cumulative reward or empirical reward, and let us say it is 0.8. Okay. Somehow, if I can bound the difference of these two quantities according to the number of samples, then I am in I have something.
So if I had infinite number of samples, I will learn points.
Exactly.
fewer samples means I'm away from body.
Exactly.
So I want to, it's a trade-off.
And this is captured by the Hofting's inequality. Okay. So what Hofting's inequality tells me is that this is the empirical reward that I have. This is the true reward. Expectation is nothing but true reward. How much it deviates from delta, some quantity delta, is basically bounded by e to the power minus 2n delta square, where n is the number of samples that I took. If n goes high, this probability goes down.
What was the name of this inequality?
Hofting's inequality. Does it make sense? Now things are easy, right? Okay, question? So now what I can do is, based on this inequality, I can find some bound on the estimated mean mu I and I. So what is mu I hat and I? It is the empirical reward of arm I if I have collected Ni samples of it. So when I say I have collected Ni samples, that means I have pulled this arm Ni number of times. Okay. What this will be? This will be again same thing. X bar is nothing but empirical reward, mu I is nothing but expectation of this, is greater than equals to delta, will be less than or equals to e to the power minus 2 Ni delta square. This is easy. Okay. This is what I had the last line in the slide. Now what I do, I just somehow magically I substitute my delta to be this square root 2 ln t by Ni. Why I am substituting, it will be clear based on when we do regret, but right now just assume ki magically I have done this. Okay. If I substitute this delta, I substitute delta and I get this t to the power minus 4, which is pretty low if t is very high. Okay. And this is good because it tells me as t goes higher and higher, the probability that the estimated mean will be very much, this should be mu I, sorry, my mistake. So the estimated mean is very high from the true mean, has very less probability. Okay. And what I will do is, I will basically take this term square root t ln t by Ni as my term which I will add to my mu I hat. We said that, right? On this empirical reward, what I will do, I will add some term so that it denotes some optimism. Okay. So I will add this term.
So that term denotes how far I am from the actual mean.
Depends on Ni. Yes, but some way, right? So what does it mean? So if I take mu, so for each arm I, what I am doing is, I am capturing, instead of choosing the arm with the highest mu hat I am basically choosing the arm which has highest this term.
So what was Ni? The number of times I have explored I.
Yes.
Among all n number of trials, the number of times I have explored
I,
I.
Ni.
Okay.
Okay. So this is the term that I am maintaining. Okay. And what I will do, at each time t, I will basically pull the arm with the highest this reward.
Do the summation of the Ni's become equal to small t?
Capital T. Summation of ideally,
Small t here.
my mistake, it should be Ni small t. So Ni small t basically denote the number of times arm I is pulled till time t.
Small t.
Small t. Yeah.
So this is where the greediness of the algorithm is coming from. You are pulling the lever with most optimistic.
Exactly.
You're hoping that that is the true, it converts to that.
Yes.
So this assumes that each of the trials have this IID property, right? That's
Yes. It is assumed. If that doesn't work, it doesn't work. So if IID is not there, we will have to go to something called Markovian bandits. Thanks for pointing it out. We assume that the rewards are IID every time I pull the arm. That's the independent and identical. The rewards are coming from independent and identical distribution. Identical because this mu1, mu2, mu3 are fixed, and every time I pull the arm, the sample is independent of the previous sample. Okay, perfect. This is the algorithm that we talked about. Simple, eh? I mean, you're just assuming some optimism and just taking a leap of faith and pulling the arm with the highest optimism. Ki, you know, this is the best thing. You're basically choosing the person to the highest capability.
So, why is it best to set epsilon equal to 1 by t, why not 1 by t square or something else? We have to optimize there also.
So, with one, yes. So, what happens is, if you prove the regret guarantees, I haven't gone into the detail, it turns out that 1 by t does a reasonably good task. Okay. Again, you may get something, but asymptotically it doesn't matter. 1 by t is as good as 1 by t square. I haven't gone into that. Questions? Okay, I will skip this. What I want to do is, how long can I go? 5 more minutes. 5 to 10 minutes I will stop, okay. So, the thing that I want to do is just again trying to give the intuition, how do you prove the regret? This is where the math is coming, okay. So, but the idea would be simple. The idea would be to bound the Ni. So, basically remember the way we wrote the regret, it was summation over I equals to 1 to n. I changed the notation, I am really sorry about it. So, it was capital Ti into n, now we have Ni into mu I, right, sorry, delta I we have, right. So, what I want to bound is, I want to basically bound the number of times I am pulling a suboptimal arm. If I can do that, this I am done, okay. Either I am doing that, or I am saying that even if you are pulling suboptimal arm, that suboptimal arm is reasonably good. That means, even if you end up in selecting mu2 instead of mu3, you are only making a regret of 0.2 instead of you would have selected 0.1. Okay, this is where my dilemma is. Okay. So, what I will do is the following. The first observation that I make, suppose at a particular time t, instead of mu3 here, I ended up in selecting mu2. Then when will this happen? Exactly. So, mathematically it means that your mu hat I Ni plus square root 2 ln t by Ni, this term is greater than or equals to this term, then only you will pull I. Yes, we all agree based on the algorithm. Okay. This is the tutorial question. Okay. What you can do is, although I was planning to, but let me skip it. What you can prove is that, and it is not a difficult proof, if this happens, then at least 1, 2 or 3 should happen. Okay. So, how will you prove this? You will assume that, let us say, neither 1 happens, nor 2 happens, nor 3 happens, then you will get a contradiction to this. So, please prove it in your tutorial session. Okay. I will come to it. Okay. So, meaning of this is, the first term is saying that the empirical reward of I star, the best arm, is lower than the true reward minus this term, which was your lower confidence bound. Okay. This term is saying the empirical reward of this arm is higher than the UCB term. This was your UCB, this was the lower. So, plus is the upper bound, the minus is the lower bound. Okay. And third term is saying that this is happening. Okay. Ki mu star and mu I ke beech, so the difference between mu star and mu I is too high. Okay. So, any one of this should happen. Okay. Now, first and second you can bound. How? Hofting's bound. Hofting's bound. the difference between this and this is greater than this, is less than equals to e to the power something something, which is t to the power minus 4. So, this happened with probability t to the power minus 4, which is low. This happened with probability t to the power minus 4, which is again low. So, these two are taken care of. Okay. The only bad condition is this. Okay. Now, again tutorial question, what you can, this is done, what you can prove that if I have large enough samples. So, if my number of samples is greater than 8 ln t by delta I square, then this cannot happen, where delta I is the difference between mu star and mu I.
What is n star?
Sorry, n star is the number of times you are pulling the optimal arm. It should be n I star, yes, it is n I star, sorry. So, this should be n I star, okay, perfect. Okay, so this again you can prove just by just substituting ni to this, and you can prove that this will become, this will lead to some contradiction. Okay.
What's the difference between mu hat I star, ni star, and just mu star?
No, I just define mu star, right? So, mu star is,
That's it.
no, mu star is the actual mu. Mu star is the mu I star. Okay. So, mu star is the equals to mu I star.
Okay, correct.
That is mu star.
Okay, mu hat.
And mu hat I star ni star is the estimated reward of the optimal arm. Okay, and n star is nothing but ni star. Now I guess it should be okay. Okay, good. How will you do this? This is simple. You basically wanted to bound mu star minus mu I plus 2 square root 2 ln t by ni. Okay. So, mu star minus mu I minus 2 square root of 2 ln t by ni is equals to, again I do not know why this SI is there, but it is basically ni is greater than 8 ln t by delta I square. Okay. So, this term will be greater, so 1 by ni will be less than this and minus is there. So, this term will be greater than mu star minus mu I minus 2 square root of 2 ln t divided by 8 ln t by delta square. Okay. So, you will eventually get, so 8 will cancel out, you will eventually get delta I here, t again you can upper bound by capital T. So, everything will get cancel out and you will get minus delta I. Okay. And this term is 0, sorry, this mu star was nothing but mu I plus delta I. So, therefore, this term will be 0. Okay. We can do it in tutorial session, but is intuition clear? Okay. So, now once you have these terms, okay, we can work out the math in tutorial, but once you have these things, then what will happen is that now you know how many times you are pulling the suboptimal arm, and this gives you the regret. Okay. So, what is due to suboptimal pulls? So, 8 ln t by delta I square denote the number of times you would actually end up, the worst possible number of arms times you will basically end up in pulling the arm I from here, right, and how much regret it will lead to? It will lead to the regret of delta I. Okay. So, this gave me summation over I 8 ln t by delta I, and that gives you the regret guarantee of log n, log t. Okay. Now, one thing that I will end the session here by just saying one more thing. One thing that you can ask is the following question, whether this is good enough. We got some regret, okay, whether it's a good algorithm or bad, and that leads to the lower bound. Again, proof I am skipping, but the lower bound also says that the best you could do is getting the regret of log t. So, you can easily come up with the two distribution that no matter what algorithm you will use, you will at least end up in taking log t number of rounds to distinguish between these two arms. That is the idea. So, this is the best possible asymptotic regret that you will get.